Hello guys, today in this video we will deep dive into the loss function in generative adversarial network. Before moving to the loss functions, let's spend some time on the generative adversarial network and recap some concept reasoning. So this is discriminators and this is generator, the two main components of the generative adversarial network, and this is the sampling space or Latin space is from where we sample the noise vectors and it passed to the generator and generated some samples, and this is a real data set, and we pass through this both the images or data, and discriminator will predict this whether it is real or fake, and it will even fine tune itself not only fine tune but update the parameters of here is in here, and it will update the parameters of here. So both the parameters will be updated as any, and all the words and biases will be updated from here and here, according to the feedback by the discriminator. As in, it will update the weight of generator, and also the output of the discriminator helps to update the weight of the discriminator itself. So there are basically three types of loss in generative adversarial network. One is min-max loss, another is in modified min-max loss, and another is Wasserstein loss. And we will deep dive into all these loss functions. And let's first of all look at the min-max loss. This is the min-max loss. Let's This is the objective of the min-max loss, and we will deep dive into this is in this loss functions, and we will derive it from scratch in the copy. We will continue the loss of GANs from now. So I will explain in my copy so you can easily grasp the concept. So this is discriminator and this is generator his name. We are the sampling or random vector z from Gaussians or any prior reasoning and passing through the generator and generating this g of z, which is a fixed sample, and this is x, which is a real training data, as we are passing to the discriminator, and discriminator is producing the giving the probabilities whether this is real or fake. And this is the discriminator. D is what is D is the discriminator probability output for this given input, and this x given input. So let's derive the loss functions from scratch of of the GANs. So first of all, I want to this is our discriminator, which is just a binary classifier, isn't it? So binary classifier try to classify the real or fake images, isn't it? So we have already studied that, isn't it? The loss function for a binary classifier is y log of y hat plus 1 minus y log of 1 minus y hat. So what our objective here is we want to make the loss functions of this GAN. So we will first of all try to learn from the first principle. So we will not directly writing down the objective function. So first of all, this is a first time we are building, think like we are building this network. So first of all, this is our discriminator. We doesn't know about any objective of this network, whole network. And so first of all, think that this is discriminator. So discriminator have some, this is discriminator, and our main objective is to make some objective functions for this whole network. So first of all, we are just focusing on the discriminator, and discriminator is just a binary classifier which will classify the real and fake, isn't it? So what we'll do is
just give the label y is a real real is label real label or original label. Y hat is a predicted label, so predicted label is label. So and this is our to output, this is our to output, this is our for generated image. This is y hat, we have two y hats, isn't it? So this is d of x and d of z, isn't it? For those for the for d of x, isn't it? We can, the d of x is the real output, isn't it? So it should be 1, isn't it? This is a real, so this is a discriminator probability for the real data x, isn't it? So that should be equal to 1. And isn't it? This is d of z, means this is z of z is a fake data generated by the generator, isn't it? So this should be is equal to 0 for the discriminators. To build a better discriminator, we have to make this quantity is equal to 0 and this quantity is equal to 1. So this is our y hat, isn't it? You can imagine this is our y hat, and let's apply the loss functions. So this is our y hat, isn't it? Y hat to y is in, and this is the same loss function as I've already wrote. So this is a two variable function, so you can, so I will write it again, isn't it? So 1 minus y hat, and first of all give the label, listening, give the label d of x, listening. For the real, we'll first will do for real, listening, d of x 0. This is our real label, listening, because the d of x is not 0 but 1, listening. So for real level this is 1, and what will be, what's value, it will value will be, listening, log of d of x. This is our predicted, this is our real should be, its predicted value should be 1. So this is the loss functions. Oh, it's not showing here, so I will move it. Oh, so this is in so this is a log of d of x. So this is our, it's fulfilling for one y hat, we get two y hats. So for one y hat, we get d of x. This is for this is the loss functions for those for d of x. And for the another input, for the another input, l y hat is in comma y, and this y hat will be d g of x, guys, is in. And this is real level, this y is real is 0, it should, discriminator should give this 0, isn't it? So what we'll do is y is equal to 0. So what will be its value, isn't it? So it's 0 means, isn't it, we are giving y as 0 means this quantity, this up quantity will be 0, this quantity will be 0 for this, isn't this, and because the y is 0, so this quantity will be 0, and 1 minus 0 will be 0, 1 minus 0 will be 1, and log of 1 minus d of g of x. So we arrived at these equations, and so 1 minus d of g of x, this is not x actually, this is z, d of z. So this is our second objective for the generator. So tell me this thing and tell me and just try to, first of all we combine this both loss, and I will tell you what to do. This is our, oh, it's not all showing, and this is y hat y is d of z of x 0 1 minus log of d of z of x, and this is just see here and understand yourself. So guys, we have arrived at these two equations. First equation is what are first equation we have? First equation we have the loss is the d of x comma 0, and another is 1. This is not 0, this is 1. D of g of z, we can just give x, but doesn't matter, and this is 0. This is our first loss, estimate what is this value is ni, this value is log of um, log of is ni, d of x, and this is I think 1 minus log of 1 minus d of g of z. So guys, this is our, these are both functions, and so these are lost. We have find these equations 1 and 2. This is suitable, and this is suitable for the, this is suitable for the discriminator. So discriminate, this satisfy the condition of discriminator. When this is equal to 1, this equation hold like this. When this is equal to 0, and the equation hold like this, isn't it? These two equations satisfy the discriminator conditions. This is means the probability when x is real means it should be 1, so we get these equations. When this generated data, this is g of z is equal to generated data, and when it passed to the discriminator, it should be equal to 0 for the discriminator. So we get this equation as from binary cross entropy formulas. So, and let's combine these two formulas, and if you combine this, we get this log of d of x loss is in log of 1 minus d g of z. In some literature, you find this z as x, but you can consider it as z as in. So these are value functions. This is our value function. So you can write this. This is the loss function. This is our final loss function. We can, and what we will do is and this is our final loss function. So what we will do is try to think would you maximize these loss functions or minimize these loss functions? Just think and tell me. This is our loss function. So for the discriminator, for the discriminator for LD, I am writing LD for the loss for the discriminator. Whether this loss function should be minimized or maximized, tell me guys. This is d of x. This should be high. For the discriminator, this quantity should be high because the discriminator probability for the real data should be high. If this quantity, this inner quantity is high, the log of this inner quantity will must be high, so, and this is 1 minus d of z of z, so this quantity is, if this quantity is higher, if this quantity is higher, d of g of z must be low, low. So the probability d of z of z means if d of d discriminator output for the generated data points, generated data point be is equal to low, it should be equal to 0 or low, low. So if we maximize this, if we maximize this loss objective, we will get, so if we maximize this, we will get our objective accomplished. So if we maximize this quantities in this quantity, this log of this quantity and this quantity, if we maximize this both of these terms, we will actually eventually get our discriminator objective is complete. It is giving high probability for the real data and giving low probability for the generated data. And if we I think you understand this is what is happening here is log of 1 minus d of z, if it becomes 0, 0, it becomes low, and this quantity will be higher, log inside the log will be higher, inside the quantity. If this become very low, and this quantity, second quantity become low, this whole inside thing will be maximum. And if this maximum was the log of this quantity will also be maximum, because loss the monotonic functions. So you can see there, as the value increases, and as the value of x increases, it's also tending to increasing. So this is a log will be increased. So this is the property. So, and for the discriminator we conclude right now, we want this become we want to this become maximize isn't it? We want to this make maximize, and for the generator isn't it, what we'll do is, guys isn't it, this is the plot isn't it? This is, I am just taking this log of x as y-axis and d of x as x-axis, and this quantity upon y-axis and this quantity upon x-axis. For the discriminator, we are talking of discriminator. Discriminator is just a binary classifier. Discriminator. For discriminator, we want this quantities. D of log of d of x is equal to log of d of x is equal to, we want to make this quantity bigger, or we want to make this quantity as this inner quantity is equal to 1, because this is a real data, and discriminate, if this is a probability of real sample given by the discriminator, it should give 1, d of x should be, must be 1, when d of x is equal to 1, d of x is equal to 1, this is, I think, this region is, because this is a probability, understand, d of x is a probability, so it can't be, it can't be exceed more than 1, and this d of g of x is also probability, it can't exceed the value of more than 1. So if you trying to just, this is from 0 to 1, this is 0 to 1, and this is just a function, this is a function, and this is a, we have this function has just a range between this and this, because this is a probability, so it can't exceed more than 1. This is, you can just think this is a restricted zone, we are not probability, and we have to find the maximum value of this function, the maximum value of the function lies here, here, because this is a negative, so this is 0, when log of d of x is tending to 0, this is the maximum value of this function, or this is the maximum point of the of this d of x, so this whole, not a d of x, but this whole log of d of x, it can have maximum value at this here, when d of x is equal to 1, the maximum value is this, so we are maximizing, you can understand that, if we maximize this function, we certainly get here, here, we can't go here, and if we maximize, trying to maximize this function log of d of x, will ultimately reach here, this is the intuition, so this is a, I think you can just, this is a parameter, as you optimize any function, and we want to we want to find this optimal value, this optimal value is 1, so if you maximize this, we will eventually get here, like that, so for another term, this, and I'm plotting like this, and for this we want to make this as 0, this is for, we want to make this quantity as 0, and for this quantity we want to make a 0, so if you, this is log of d of x, so this is 0 and 1, we want to, what we want to do here is, this is our discriminator, we want to make this quantity as much as higher, higher, so that this quantity d of g of x become, this quantity becomes 0, and if we maximize this, if you try to maximize this quantity, what we will get, just imagine, if you maximize this quantity, we will get this value as here, if you try to maximize this function, because this is restricted, we can't go here, but this is just, we have this range from 0 to 1, 0 to 1, if you maximize this function, it's not, we can't just here, just see what the maximum value of this function is, this function log of d of x, maximum value is this 0, so if you maximize this curve, this curve we will end up here, end up here, in which d of g of x is equal to 0. So if you just maximize this quantity, this function, will end up being here, because this, because if you optimize, if you going from optimizing this and reaching this optimal point of this curve, this curve, we will eventually reach here, where d of g of x is equal to 0, which must be, because this is a discriminator should give this g of z is equal to 0, output, this is a probability discriminator output for the generated image must be 0. So we are end up in here. If you maximizing this curve, we will end up here. So let's derive the loss function for the generator. For the generator, we have already derived the loss function for the discriminator. If we minimize, if we maximize this function, this objective, our discriminator objective is fulfilled. If we maximize this quantity, our discriminator objective will be fulfilled. So for the generator, for the generator, let's try to derive the objective for the generator from this discriminator objective. So for the discriminator, for the generator, we does not have access to this term, because log of d of x, we does not optimize for the for the generator. This value, this value is not available. D of x means this is real data. X means real data, so we does not have the access to real data. So we will remove this term. So we will remove this term, and we left with e z sample from p of z log of 1 minus d z of z. So this is we arrive to this equation, because we doesn't have, we are deriving the loss for the generator from the loss of the discriminator. So we doesn't have the access of this term, so our objective become this, isn't it? So our objective become this, and think, uh, for the generator, we want to make this quantity, this quantity equal to 1, we want to make this quantity is equal to 1. When the generated image is passed the discriminator, we want the generator discriminator to output this 1. So if we look at here, and what happens, if we minimize or maximize this condition hold, if you minimize or maximize this objective, the d of x, d of g of x become 1, if you observe that, if we minimize this, if you try to minimize this, this objective, whole objective, this this term will push to become 1, 1. So if you try to minimize this function, minimize this objective, so we will certainly reach d of g of z is equal to 1, because 1 minus something. So this term would be greater, for this function this value should be higher, nearer to 1 to become this quantity to lower. So because log is a monotonic functions, and for the graphical approach, let's see it, I have plotted this, I have plotted this d of g of z and along the x-axis, and this is along y-axis. This is the function, and if we see, you can see, if we, this is the d of g of x in x-axis, and this is the curve, this curve is this, is in this objective is this curve, so this is, you can, this objective is this curve, and you can see this curve, if we is minimizing this curve, from this maximum value, it can hold is 0, 0 and 1, so this cannot be exceed 1. So if we look at this curve, so this is the curve, and this region we doesn't have the access to the other region, because this is the probability, we can just around 0 and 1. So you can see here, because the d of g of x can't exceed 1, because this is the discriminator probability, for this images. So if we look at this region, and if we minimize this, and if we minimize this curve, we will eventually, if you minimize it, go down, because it's a negative. So if you down it, the value will be more below, more low, or minimize, you go down. If you minimize this, we will eventually reach, it will eventually reach the corresponding here, 1 nearer to 1, it will asymptotically, it is going down, so So if we try to minimize this objective, this objective, we will eventually reach, we will eventually reach the reach our d of g of is equal to 1. So our objective is fulfilled, and let's write the combined form, combined form for both of this. So look at the combined form of the loss, so e of x sampled from, this is the loss, so min max loss. So generator we want to minimize it, and if you combine this both of this term, and log of d of x, and z sample from the prior, and 1 minus, and log of 1 minus d g of, guys, you can see here, and this is the log of g of z. So this is our objective, guys, this is our entire objective, you can see here, isn't it? So we have to, we have to maximize, maximize this, we have to maximize this according to the discriminator, and we have to minimize according to the generator. And while minimizing the generator, while minimizing, we will not consider this term, for the notation we write it, for the compactness, for the compactness we write it, so to represent the both the things. So if we can just remove for the generator, but you can think like that, if we are minimizing with respect to generator, we will not consider this term, will not consider this term, or we will remove this term, and for the discriminators, we will consider the both of these terms, both of these term. And this is the compact representation, of the losses, loss of GAN. So if we have to accomplish this objective, so this is the MinMax loss, and we will move to the modified, modified form of the MinMax loss, because this term is here, for the generator we have to modify the generator loss. So we'll see, what to do, before that, I want to just give you again, I want to just tell you, this objective again, so what we are doing is, actually we are sampling the axis, we are sampling axis, from this known data distribution, and passing to the discriminator, and calculating this log of dx, and we are sampling the z from the random vectors, from the some standard distribution, and passing to the generator, and then passing to the discriminator. And if we minimize this, to accomplish, to make the generator capable, to make the generator better, we have to minimize this, we have to minimize this objective, and to make the discriminator capable, we have to maximize, to make to make the discriminator capable. So, and first of all we maximize that, we maximize this objective according to the discriminator up, and after some epochs we will minimize this objective, and we again, maximize the discriminators in this objective with respect to discriminator, and discriminator become most more capable. After that we will minimize this objective, while minimizing this objective we will not care this term, so we just care on this term, because we doesn't have access to the data, generator doesn't have access to the real data. So when, and then after that we will minimize this, and generator become better, and we will repeat this process, and our objective will be fulfilled,
Guys, the loss we have already, the min max loss which I have already discussed, actually does not work well in practice, we have to modify the min max. We have to modify the min max loss. So we'll introduce this min max loss, and this objective is this, this is the objective, same objective, the X from the real data, and from Z from prior. This is the same objective, but guys, there is a change, there is change. we will not use this objective anymore. In practice, this objective for the generator does not work well. So why it doesn't work well is because when our level when our sample is fake, when our sample is fake, the gradients here are very flat, and which will not help the generator for which will not help the generator to become better. So this generator objective is in here is not work well. So because this is flat, when level is performing very bad, when generator is performing very bad, the signals are not effective for the generator. So this loss trajectory, this loss does not help us in this optimizing. This does not help us. And guys, what's measurement? And we want to and here when when our generator is doing pretty well job and class and fooling the discriminator and fooling the discriminator at that giving level as one, discriminator is giving the level as one, the gradient signal is dominated here, as you can see here. This is not a flat, this is pretty dominated signals here, and we can get from here. And so there are some flat signals, so it will not. So our optimizations will not work well as in if we apply this loss function. So what we're gonna go do is we'll just modify this loss, isn't it? Not we are not modifying this discriminator loss. We're modifying this generator loss. And how can you modify it? Isn't it? Let's see. So here is, isn't it? So this is the our original one, isn't, and we'll modify this, isn't it, by this loss functions which call with this, isn't it? And what we're doing is, isn't actually we are in the previous case we are minimizing, isn't it? Minimizing the discriminator being correct, isn't it? We are minimizing if discriminator being correct, isn't it? But now maximize the discriminator being wrong, isn't it? We are maximizing this kind of being wrong. So the objective is same, but we are moving in another direction. Our goal is to fool the discriminator. So same objective of fooling the discriminator, but now gradients, higher gradients signals for the bad sample. Or if the generator is producing bad samples, so it means generator has to learn, generator have to learn, if it is producing bad samples, so we have to learn. So when discriminator giving level 0, the training signal is dominate high gradient signals which help the generator to become better, and when the generator is doing good job, we already doing good job, so the signal we does not need such a dominated signals, and this is relatively flat, we need it's better, so for bad signal, but now higher gradients for the bad sample work much better standard in practice. So this is the modified GAN loss, guys, and this is a core trajectory, as you can see. For the when discriminator giving level 0, the signal of this curve is pretty high. The gradient here is pretty dominating. So it will help. This signal will help the generator to become much more better because it is doing some wrong job, and the gradient signal is higher, and this higher gradient signal will impact the generator to become much more better, So that's it, for the min-max, modified min-max loss. Let's discuss about Wasserstein loss, So, Wasserstein loss is the distance measure between those two distributions in the data distribution and the generated data distributions, So, in this, we want to minimize the loss, What is loss here? Loss is the distance between these two distributions, we can take the example. This is Q is the distribution of the generators, and this is the real data distributions, we want to minimize this losses, and loss means the distance between these two distributions, so it is a better matrix, isn't it, of measuring the two distribution than using the previous, min max loss, isn't it? enable us isn't it, to isn't easy to easily distinguish the matrix isn't it? It's also better matrix for doing isn't it? For knowing the isn't it? The state of the generator isn't it? And it improves engineering dynamics isn't it? By leveraging Wasserstein distance to measure the difference between real and generated distributions isn't it? The training dynamics is better isn't it, of it isn't it? And here isn't it, we he does not use discriminators but you can call this critics, we call discriminator as critics so and this is not a probability this is not a probability it does not output a probability, it's a real value it outputs some real value so it can be it is not, its value is not bounded between 0 and 1 it can have a value between 100 5 and 20 so and it gives isn't it? This D gives in discriminator gives in it, discriminator critics isn't it? Gives isn't it? Lower values in it for the fake data and higher values in higher value for the real data isn't it? And the discriminator try to maximize this function because isn't it, if critics if discriminator gives higher values and higher values lower value to this and bigger value to this and the difference should be maximized isn't it? So critics try to maximize this function isn't it? In other word it try to maximize the difference between its output on the real instance and its output on the fake instance and generator try to maximize this is generator try to maximize this means uh, when the fake data is being passed to the discriminator generator wants to maximize this output of the discriminator isn't it? So in other words try to maximize the discriminator output for its fake instance and if you combine both of this isn't it? If you combine the above and this in a batch of data isn't it? Novel Basavitas and this expectation come here as in expectations also come here as in we are sampling X from the real data distributions and sampling this X tilt is in from the prior is in originator distribution is in so and we are passing through this discriminator is in discriminator this X tilts means exactly this inner quantity is in so when it pass through a destiny and the discriminator want to minimize this isn't it? And generator want to minimize this but discriminator want to maximize this isn't it? Why generator want to minimize this here you can see that this is maximizing here isn't it? And here is minimizing but isn't it? We are not maximizing this isn't it? We are not we are maximizing this but we are minimizing this difference we are minimizing it because if this output is high isn't it? High isn't it? As close to as this isn't it? The difference will be minimum so we want to keep this as much value as for the real instances so it value will become higher and this value is higher because this is a real instance so the difference will be minimized isn't it? If this is convincible this convincible image is an image or data isn't it? So and we want to maximize the difference in a discriminator want to maximize this difference so that so that it gives lower values for the fake instances and higher value for the real instances and there is a and to we use some constraint here in the discriminators the discriminator this is our critics should be the set of any one listed functions any we impose listed continuities in here is in here and we'll go on deeper on that later on. So first of all, what are the advantages in using this as any? It provides stability. Stability critics provide smoother and more informative gradients, leading to better learning dynamics. Yes, isn't it? And it prevents it mitigates the problem of mode collapse. Means where generator produce a little variety of outputs, so it can mitigate the problem. And we will look at it as an here as in we have two approaches as in to impose this constraint as in the to make this as in discriminator or set of one Lipschitz function as in we impose constraint as in first of all we clip the weight of discriminators and we clip the weight of discriminators in the between 0.001 to as in minus 0.001 the weight of discriminator can have within this bound as in so that we impose this is any set of one Lipschitz Lipschitz functions is any because is any if you up if the discriminator becomes the set of one Lipschitz functions any it it helps the generator as any with better gradients and as any I've also as any I want to also show you something as any so what is Lipschitz continuity is any it's a mathematical property that measure how fast a function can change as its input changes. In context of GANs, it is desirable to enforce Lipschitz continuity on a discriminator functions isn't it? To ensure, isn't it? To ensure that it does not change too quickly and cause instability during training. Isn't it? So it's provide better stability during training. Isn't it? Training. So we use Lipschitz continuity. Isn't it? So and this is we are clipping isn't it? We are enforcing this Lipschitz continuity isn't it? Continuity on the discriminator functions by clipping the word of discriminator or critics isn't it? We are just bounding the value of discriminator between 0.001 to minus 0.001 and we are just assigning we're just bounding the weight of discriminator so that it enforce this constant the Lipschitz continuity isn't it? So that so here is the algorithm asini. This is WGAN asini. WGAN without asini gradient penalty asini. It use clipping method asini. Instead of asini, uh, this is 0.001 asini. This is clipping method asini. Instead of gradient penalties. And let's understand this algorithm because it it helps to better understanding of our lesson learning. So this is purpose algorithms any the parameters they have given this alpha learning rate given this and this is a clipping parameter I have telling you c is equal to 0.001 0.01 and this is batch size and this is the number of iteration for the discriminator to train at we first of all train discriminator for 5 times critics for 5 times then for generator and then 5 times discriminator we train and then train the generator this is the and critics we use 5 times so this is and critics and what we are, this is as I have told, alpha is equal to learning rate, clipping parameter, batch size, and the number of iteration of critics per generation iteration as any number of critics iteration per generation iteration means we do have number of iteration as any per one generation per generator iteration as in. So and w naught is the initial critics parameters and theta naught is the initial generator parameters. This is the weight and biases of this network as in. This is critics discriminator and generator parameters and we are applying this outer loop as any outer loop from here to here as in here to here and from year to year and so inside this we are applying this thing is in these things in a while theta is in theta is the generator weights in hasn't converged is any if the generator weight hasn't converged do is any what to do is in here is in from 0 to 5 is in 0 to 5 do a sample real data from the training data sets and sample the prior listening from the noise distribution or simple listening like Gaussian or any prior listening. Prior means isn't just a standard distribution from where we sample it and pass to the and what we have to do listening and we have to take a gradients of this as in loss function as in what you have defined here and we feed this and apply the gradients, and apply the gradients, compute the gradients, and what we do, we apply this as an, we add this because we want to maximize it. So we apply this alpha times, isn't it? This optimizer, we apply this RMS drop optimizers and update the words, isn't it? Update the words, and we do clipping here, isn't it? Clipping means, guys, isn't it? We doesn't want the value of the words of discriminator too much, isn't it? We are just bounding between 0.001, this 0.001 to minus 0.001, isn't it? So within this value, isn't it, the discriminator word should be, isn't it? Should be, isn't it? So it enforce, if you do that, it enforce the listed continuity is any, and which is necessary. Why listed continuity is necessary? Because it allow us as any to get better training stability, and it solves any like problem like mode collapse, and we have discussed any. But and there are other benefits also, any. So and after that, what we'll do is actually listening, and we sample the noises, any noise from the prior samples. We just sample the noise, and this is time for generator training. So we pass this only, not real data. We just pass the samples, as any the generated sample, and pass it through, and train the passes the discriminator, and we doesn't update the weight of discriminator and update the weight of generator z theta as any. This is the weight of generator, and we compute the gradients, and we calculate the gradients, and as in we apply, because we want to minimize this, so we apply this as an RMS probe was any, and this is learning rate times this optimizer values in it. So and we do in while as an in while, and if as an if theta has converged any, if theta has converged, we exit of the loop and our process will be completed. If theta is not converging, isn't it? Theta is not converging, this theta value is not converging, we again repeat this process until theta has not converged, isn't it? So this is without, isn't it? This is, we are clipping, isn't it? We are clipping the weights of discriminators, isn't it? So while clipping, isn't it, guys, isn't it? It produce some undesirable results, isn't it? Undesirable result, because we are bounding the value of the discriminator or critics, isn't it? If you bound this undesirable property will arise, isn't it, in the critics and the gradients, the if you apply this in the learning dynamics will get affected as well, listen, because we are clipping it, but it's not a good thing, is we are bounding, this is a hard constraint, is we are imposing, isn't it, on the discriminator weights. So isn't it, so it does not give us any better results, isn't it, better results, and it does not help us any the generator to become much more better, isn't it? So how can you find the better approaches, and instead of just bounding the valuation into the of discriminator, rather than we use some another approaches any called as any gradient penalties any. Let's discuss about this with the gradient penalties, this is what we do here is actually, this is the same as same same the previous is any WGAN loss, but what we're doing here is just introducing this gradient penalty term as any term. There is this lambda as any, and let's talk about the as any notation as any what we are going to be using here as any. This is x tilt means the generated distribution data as in generated distribution data, and this x is the real data distributions, and the data sample from real data distributions, and this is x is in. So and this is x tilt, this is the combination of this x tilt and x as in. There is some, if you apply the linear interpolation as in between this and this is in like this, in linear interpolation here is in here, if you apply this linear interpolation here is in, we will get this x tilt, uh, and we are applying this term as in. So let's discuss with it as any WGAN with gradient penalties any. We we have this as any parameters lambda is equal to 10. Lambda is as any, lambda is this gradient penalty coefficients, and the number of critics iteration per generation iteration is n critics. Batch size we are taking m, and some atom hyperparameter alpha beta 1 beta 2 is, requires an initial critics parameters this, initial generator parameter theta not while theta hasn't converged do. Theta is the generator parameter. So until it has converged, we are running this inner part. So first of all, we are running this from 1 to 5. And critic is 5 and 2 is any, and from for I to 1, for the whole batches of data is any, we are sampling is any x from the real data distribution. We're running this loop for m times is any m times. So m times for, and we are what we're doing, we're sampling the some real data from the real data distributions, and sampling this z as any from the latent vectors and from this prior, and this is epsilon as any, which is which we are sampling from this set as any. So and we are passing this z to the generator, and we are obtaining this x tilt, and we are applying this x, we are applying some linear interpolation here, guys, isn't it? Linear interpolation means just combination. We are just combining this both of two worlds so that as any we can capture the whole space as any, and this x tilt becomes as any epsilon into x plus 1 minus epsilon the x tilt. And as any, we are as any, we need to apply this as any, we are to apply this x tilt to the, why we are not, why we are applying this here as any x tilt. So what we're doing here is just defining the losses in dw, dw of tilt minus dw of x plus lambda, and this term, this is a gradient penalty term, this is the same term, and this is a gradient penalty term. And what is this term is actually is this is norm 2 of the gradients of architects, isn't it? And we want to make this quantities in less than 1 or 1 is at most 1 or less than 1, so that we enforce the Lipschitz continuity in our discriminator functions. So if you enforce that as in, if you make this quantity 1 or less than 1 as in, we enforce the Lipschitz continuity in our functions. And if it does not obey that, we will this is a penalty coefficient and lambda as in, and it will enforce any this, if you apply in the loss functions, and it will enforce the discriminator to be listed continuous as any, a set of one listed continuous as any, because the type is one listed continuous. So if you apply this, then our discriminator will be is any one listed continuous, and we are updating the weight of discriminator as any, computing the gradient and updating using atoms and so we're applying atom optimizer here as this is our parameters. After the weight updation of the discriminator, we update after nearly after 5 times running this inner loop, we update the weight of the, we sample some sample images, and we compute the gradients and apply atom optimizers, and we calculate the weights of the generators, and we again we again run this loop until theta hasn't converged. If theta has converged we will end this part and our generator is ready for the generation.